Wendy Butler is a science teacher at St James's Catholic High School in London. Having demonstrated some exciting chemistry to her Year 11 group, she's off to CLEAPSS to seek further safety advice.
I'm coming to CLEAPSS today to see Bob, who's the chemistry specialist for health and safety, to get some advice on perhaps why my experiments didn't go exactly as planned, and hopefully he can be able to advise me on how to do them in a slightly better way, especially the screaming jelly baby and why it actually came out of the test tube, and why the methane bubbles weren't working as efficiently as I'd hoped them to. Can you tell me why my jelly baby jumped out of the tube?
Well, I have an idea that the potassium chlorate was solidifying as you put the jelly baby in. So we'll try and replicate that.
Okay.
Bob prefers to do this experiment in a well-ventilated open lab because no toxic fumes are generated. However, a safety screen must be placed between the students and the experiment.
Looking at this is very similar to what happened before. One of the concerns was to ensure that it had all melted and it was ready to put the jelly baby in. I think also being concerned about where the class were behind me would have slowed things down.
Yeah.
Now that was at the point at which...
You turned off the Bunsen?
Yes, I think that's what happened.
Okay, so let me just take that away then. Here goes then.
Although the jelly baby doesn't jump out, there's a lot of spitting and juddering inside the boiling tube.
The reason for it jumping out, I think, made perfect sense when I'd actually thought back to what I actually did in the classroom. Having a clouding around the actual potassium chlorate was, I think, the cause of me not seeing that it had actually melted. And I'm going to obviously change that and put that in with our risk assessment and take that back to the twilight sessions that we take.
Another experiment you did was the methane soap bubbles. Did you have any problems with that?
I found it really difficult. We had the tubing with a funnel at the end and put the soap mixture into a petri dish to take the soap mixture off. However, it was so difficult to actually get the bubbles to form and actually get them off the funnel.
Well, there's a recipe in the CLEAPSS recipe cards which suggests that you add a little bit of glycerol to the soap, and then we may start to get some firmer soap bubbles. And then we'll just switch the methane on. Now, you've got to wait a little while until the air has come out of the gas piping.
Right.
Ah. There we are. They're rising. Would you like to have a go?
Yeah. So just take them off.
Just cut it off, that's it. Let it rise.
This method is a good way of producing methane bubbles that are easier to control. To add to the spectacle, Bob suggests wetting your hands and letting the students light the bubbles themselves.
Oh, fantastic.
So you wet your hands, hold them at arm's length, and you have a flame.
Excellent. You wouldn't advise doing this with children, though?
No, the children can light it, but you hold it in your hands.
Excellent.
Would you like to have a go?
Yeah. Oh. When I first did the methane bubbles, it was so difficult to actually get the bubbles to stick on the funnel. And seeing Bob today using a completely different method of getting the bubbles out was fantastic. The bubbles are much, much firmer as well. And then being able to take those off and ignite those immediately was a great effect because you could repeat it much more easily without the wait time for the students. So that was excellent, and I was really, really impressed with being able to put your hands in the water and actually get the student to light the bubbles up. That was fantastic, and I'm going to use that straight away. I think there's definitely two ways of looking at the thermite reaction. The reaction that we did in school was a very controlled reaction in terms of it being in the fume cupboard. So where your fume cupboard is can actually detract away from the students seeing the total visual response from it. I see you have a safety screen here. Is it safe to do the thermite reaction outside the fume cupboard?
Yes, again, we've had reports of fume cupboards being destroyed or the glass has been cracked with the heat being produced. So you can do it outside a fume cupboard, but this method cuts down on the fume by having water to quench the reaction very quickly. Now, to make the thermite mixture, we have 9 grams of iron 3 oxide, which we then pour into the aluminium powder, and we keep doing this until the mixture is really fairly uniform. Now we put this into some fluted filter paper and put the mixture in like that. And then we make a little depression in the mixture and we place the igniter mixture, which consists of barium nitrate and magnesium powder, into the depression. Now we'll put the fuse in here, which is magnesium ribbon, and we will be lighting that.
Can I ask why you've done it in the filter paper? We've done it in a crucible within a tin with sand.
Well, with the heat, it's going to drop through there and react under the water.
I see.
And that cuts down all the fume.
I see. Right?
So we'll light the magnesium and up. Now we can come back and look at the results.
By using the CLEAPSS underwater thermite reaction, not only is smoke reduced, but after the water is poured out, the newly formed iron can be seen straight away.
We can use a magnet and we can just very quickly go into there and we just do that and you see the iron has attracted the magnetic wand. Now, take a little bit of water, just wash that, and you have pieces of iron. I would always do these spectaculars towards the end of a lesson. Well, the children will be talking about them anyway. As long as you give yourself time, give yourself at least 10 minutes to set the demonstration up and then perform it, and then might be able to answer any questions. Send them away thinking fantastic things, and then perhaps you can talk about it the next time. The handling of bromine has caused a number of accidents in schools, especially to teachers, and often we've found they've been wearing the wrong gloves. Now, the gloves to wear have a symbol on them which has a little conical flask, and they're the gloves to use, not these sort of gloves here, because if bromine gets onto these gloves, it will go through the gloves onto the skin, and as you take the gloves off, the skin comes off as well, and it's a very, very nasty burn. So we'll put these gloves
When
on.
handling bromine, as well as gloves, goggles rather than safety specs must be worn, and sodium thiosulfate solution should be at hand in case of spillage.
I found a plastic pipette like this. I've got slightly more control over using it.
Is it fine to have the fume cupboard at this level rather than all the way down?
Yeah, the specification for fume cupboards is always to be able to contain a small amount of toxic material at a face height of 400 millimetres. Now for a rather interesting reaction between aluminium and bromine. All we just take is some little bits of aluminium foil, and we'll just drop them into the bromine. Now this again is another example of a redox reaction. Now you have to wait a little time for the reaction. It's just beginning to start.
Cool.
It's the most beautiful
That's gorgeous
effect.
colour, isn't it?
Yeah, and that's molten aluminium on the surface there, possibly at around about 600 degrees.
Wow.
And you'll notice that the fume cupboard is coping very efficiently with the fumes.
I'd never done an aluminium bromine experiment before. It was very, very interesting to learn about the gloves and the use of the actual bromine bottle and the fume cupboards. I think sometimes that we can forget the whole safe picture of it all. We use bromine to show the diffusion of gases, and we also use it within the halogens at key stage 4. I've never done the aluminium bromine experiment before, so using the aluminium bromine experiment would be something additional, and also to brighten up lessons that are more theoretical, such as ionic covalent bonding, and I think that would be, again, a really good end to a lesson.
Teachers are reluctant to do some types of practical work, sometimes because of concerns about overlarge classes or misbehaving pupils. Our helpline takes something like 6,500 calls a year, of which around 15 to 20% are about whether particular experiments are banned. And in 95% of those cases, the answer is no, they're not banned, they're asking the wrong question. What they should be asking is, how can we do this safely?
It's typical that many teachers have not seen or experienced these experiments, that many of which were in books several years ago. They often think that they can't do these experiments and that they're banned, but they're not. And if you do them carefully and rehearse them, I can't stress that too much, you've got to rehearse them. When you're in front of a class, you're acting. But if they see that you can do the experiments and do them efficiently and get a good effect and a little bit of drama, then you'll get their respect and they'll appreciate it.